Yes, actually, but not yet. No, fiber optics will come up, but we're going to start with the ray model of light. Chapter 23, page 644. Now, we know that light is actually a transverse electromagnetic wave. Okay, but we've only known that for about 100 years or 125 years, 150 years, something like that. Not very. RJ, ¿cómo está? Welcome. Willkommen. Bienvenue. We've only known the wave nature of light for 100 years. And in fact, a lot of people think Einstein won the Nobel Prize for his relativity theory. He did not. He won his Nobel Prize for work on the photoelectric effect. It was a huge, huge question for scientists for thousands of years. What is the true nature of light? Is it particulate? Is it corpuscular? Is it they're little individual pieces of light? Or is it a wave? Is it wave in nature? And there are experiments you can do. In fact, if any of you study, if any of you were going to major in physics at the collegiate level, you would do a slit diffraction, where you take a tiny slit in a cardboard, you shoot a laser through it, and then you look at the diffraction pattern that it makes on the card on the other side and how it oscillates between bright and dark and bright and dark. And the only way you can explain that experimental result is if light is a wave. And if it's not a wave, you can't explain it. If it's corpuscular, if it's just little pieces of light flying through the ether or the vacuum of space or whatever it's flying through, then you wouldn't get that wave nature diffraction pattern. But then Einstein came along and did the photoelectric effect and proved that actually light is both particle and wave at the same time. That there are fundamental particles of light called photons, that you cannot have a piece of a photon. Okay? So, thank you for that big old honking monkey wrench. What does that mean? Well, point is, for centuries, for thousands of years before modern physics, light was considered a ray, and it was treated simply as a geometric problem, a geometric phenomenon. And that's how we're going to start looking at light to begin with. The ray model of light. So the rain, yeah. I'll have to try to talk over it. The ray model of light. Basically, it says that if a light is either, all light that you perceive is either emanates from a source or it reflects off of an object. And light that emanates from a source emanates in an infinite number of rays that come from that point source and travel in a straight line until they bounce off of something or are absorbed by something. That ray can, once it strikes something, it can be absorbed or it can be reflected. And light of different colors will be absorbed by different surfaces, and light of different colors will be reflected by different surfaces. A white surface is a surface that reflects all colors of light. A black surface is a surface that absorbs all colors of light. Does it actually? You look at these black chairs, you can see white highlights of light reflecting off of them. So artists were figuring that out years before scientists were even thinking about it. I don't want to get too far off a tangent, but I do want to point this out to you. It has absolutely nothing to do with anything we're studying, but I just thought of it because I made myself think of it, talking about artists. There's a movie. It was not a big movie. It wasn't a big blockbuster, but it was a really good movie. How many of you are familiar with artists, art and artists at all? Ever heard of Vermeer? Painting of his called The Girl with the Pearl Earring. Well, there's a movie made about it. Stars Scarlett Johansson as the girl with the pearl earring. And it's a really good movie. If you ever see it on PBS on the weekend or something, take a moment and watch it. Watch it for a little bit. You'll probably find yourself hooked. I bring it up because in it you see Vermeer, and you see him going through all of the travails of a typical artist back in those days, and how he made all of his own paints. And that's what artists did. You didn't go down to the art store and buy paint. You made paint, and you painted with it, and they had to come up with all their own colors, and that made them very analytical in the way they analyzed what they observed, what they could see visually, and how light reacted with surfaces and things. And if you ever look at it, if you want to think about, if you ever want to really put some thought into how light behaves, go look at some of the old masters, the paintings, the Renaissance and 19th century paintings, and back in those days before the modern art and abstract. And in Dallas, I went to a show of a traveling exhibition from the Hermitage, St. Petersburg, Russia. They brought some art and icons from Tsarist Russia, Fabergé eggs and stuff. And one of the pieces they had was a full-size painting, life-size painting of Catherine the Great. And that painting was just phenomenal. It literally looked like you could see the weave and the fabric of her dress and the light in the folds of the fabric. It's like, how could an artist do that on a piece of canvas? Have you ever, no one would ever think of, snuggling up in a nice soft sheet of canvas to sleep at night. But they took a piece of canvas and made it look like that texture. It was just phenomenal. And you'll see this a lot in many of the old masters. There's one from Rembrandt called The Night Watch that makes use of what's called dramatic lighting. Another good one to look at, just to see if you want to get a more of an intuitive feel for what we're going to be studying here in the next chapter. But we're not an art class, we're a physics class, so let's make it science-y again. Ray model of light. Have a source, light emanates in the form of rays, and they continue in a straight line until they either get sucked up by something or bounce off of it. Now, so let's start by talking about the reflection of a light ray in a plane mirror. A light ray coming in will hit that plane mirror and will bounce off of it in what's called the angle of incidence. The angle of incidence. The incident ray comes in and strikes the mirror at this angle theta relative to the normal, or to the perpendicular line from that surface. And it will then reflect at an angle of reflection. Incident and reflection? Yes, reflection. Theta sub I and theta sub R are equal. And that's basically the law of reflection. That light rays will reflect off of a plane mirror surface at an angle theta equal to the angle that they came in at. The law of reflection. Now, what can you tell about a surface by looking at the light reflecting off of it? We just talked about the painting of Catherine the Great, how it looked like all this velvet and fur and chiffon and all of these soft, delicate fabrics, and just looked so real. Well, what if you have a very rough surface? You get into it at the microscopic level and it looks really rough. Light rays coming in, a light ray coming in here hits right here at this angle of reflection, and it's going to bounce off at that angle of reflection, which means it now hits this one at this angle of reflection and bounces off at that angle. So even though it came in at this angle, now it's coming out at that angle. And another ray right next to it, just a little over, is bouncing off in a completely different direction. That's called a diffuse reflection. Look around, there's lots of examples of it. This wall right here, that's diffuse reflection. You don't see a hard edge. You see light, just kind of a smudge, a smear of light. Smoother the surface, the more faithfully, the more fidelity you will have in the light reflecting. A mirror surface, obviously a perfect mirror, is perfectly flat. So light coming in at this angle will go off at that angle nice and cleanly. And they give us an example here. Let's go ahead and work through this example, because this is the kind of thing you're going to be needing to do when you start the homework problem. We've got a pair of mirrors. That's a perfectly flat mirror. I don't care what it looks like to you. Who are you going to believe, me or your lying eyes? Second mirror is mounted 90 degrees to the first. Ray of light comes in at an angle of 15 degrees above the horizontal. It's going to reflect off and hit that mirror, and then reflect off of that mirror. So, we need to know this angle of incidence. Well, that's easy to calculate. It's normal, so this is 90 minus 15 is 75 degrees. That means it's going to reflect off at an angle of 75 degrees this way. And I would point out that that also means we could just as easily have said this 15 has to equal that 15. But you need to think about it the way the book talks about it. This one here? Show me. Oh, well, it will be, but here is our second normal. We know that this is 90 degrees, and we know that this is 15 degrees because it's 90 minus 75. We know that this is a triangle, which means since this is 90 and this is 15, this angle, the three of these angles have to add to what? For 180, which means these two have to add to 90, which means this one is 75, which means this angle of incidence is 90 minus 75 is 15 degrees, which means this angle of reflection is also 15 degrees. Now that's all a bunch of geometry and, not really even trig, just geometry. But here, if you've studied geometry, you can know that because these are what's the phrase they use in geometry? Because these are reflective, because they're equal and opposite between parallel lines, they're going to be the same. But the way you get to it is by summing these three to the 180. Because what if this was not 90 degrees? What if you were given a problem where this mirror and this mirror are joined at some not 90 degree angle? Well, now you have to be a little more careful about how you do that. Now, have any of you ever studied optics at all? Or is this the first time? Oh, okay. What can you tell me about the difference between a real image and a virtual image? Because that's what we're going to talk about, is image formation. Would be in the mirror, exactly. But not all images that you see in mirrors are virtual. First of all, let's think about what you see when you look at something. I'm just going to draw up an arrow because that's a convenient little object of the study. When you look at an arrow or a pencil or a ball or an iPhone or anything, each other, what you're actually seeing is light being reflected off of whatever you're looking at. And that light travels in rays to your eye where it passes through the iris of your eye and forms an image on your retina. Well, we're going to talk about looking at something in a mirror. We're going to talk about looking at this object in a mirror. We're going to say we're up here. That's an eyeball. There's someone's cheek, bridge of the nose, whatever, looking down at this object. Well, what is he actually seeing? You can look here at the picture on page 647, figure 23-7. And they get in here and they get really picky. They talk about, we're going to look at this line that reflects from there to the mirror and comes back and hits the bottom, passes through the bottom of the iris, as opposed to this one, which starts from the same point and passes through the top of the iris. Okay? And then they talk about the light that comes from the bottom and passes through the bottom of the iris and comes from the bottom and passes through the top of the iris. They've got a much better picture of it here on the page. Well, the point that they're making is when you extend these rays back, as imaginary lines back through the mirror, they look like they are emanating from a point back here behind the mirror. Okay? Now, is any light actually passing through the mirror? Is there any light reflecting off of something back here, passing through the mirror, getting to your eyes? No, it's starting from here and reflecting. But because this image looks to you like it's back here behind the mirror, where no light actually is, that is a virtual image. Okay? Now, I don't really... actually, I would suggest that you read this chapter and you read the part about the point they make about the difference between passing through the top of the iris and the bottom of the pupil. The top of the pupil and the bottom of the pupil, because it's interesting. But it's just a point it's a passing point. What we want to look at is the distances here. We've got, get this out of the way. We have this distance is the distance to the object, and this distance, I'm sorry, I'm labeling it backwards. This distance, which is the distance, and I still labeled it backwards. This is the distance from the object to the reflecting surface. This is the distance from the image to the reflecting surface. Okay? So, we've got these angles of incidence and angles of reflection. What they're doing is they're going to introduce a bunch of geometry here to show you that this angle from here to here is the same, this triangle here and this triangle are the same triangle. Right? And because these are the same triangle, the distance to the image is equal to the distance to the object. Well, it's actually negative. And this is something else we need to talk about, this use of the negative sign. Everybody sure they rolled up their windows? Okay. The negative sign is used by convention. Okay, and basically when you have an image distance or an object distance that is negative, it means that it's virtual. It's on the other side of the reflecting surface. Here's an example they use that I think I do want to work through this one with y'all. Really need to do the spherical mirrors. An index of refraction. Because y'all need to read through, you do need to read through section 23.4 in order to do all of the homework for this week. And so I'm not going to go through 23, I'm not going to go through example 23.2 with you. It's easy and straightforward enough. You should be able to work through it on your own. It's just about how tall must a mirror be in order for you to stand in front of it and see your full body. And the interesting aspect of it is you're going to find if you actually sit there and do the analysis, you'll find that once you've got the mirror the right height, it doesn't matter how close or how far away from it you stand, you're still going to be able to see your full height. As long as it's the right width and positioned at the right height on the board, on the door, on the wall. Now, this is a virtual image. In the back corner over there. That is a spherical mirror. In particular, it is a convex mirror. A mirror that bows in, well, that's your reflecting surface, is concave. And yeah, I remember it because caves go into the hill. A mirror that bows out, so this is the reflecting surface, is convex. Now, when you start looking at images in spherical mirrors, what's the one thing you're going to notice right away? Well, that depends on where you're looking at it, how you're looking at it, from where, from what perspective. There's always going to be some distortion. What's that comedic line or moment in Jurassic Park where the T-Rex is, about to bite the side view mirror off of the Jeep, and it says objects in mirror are closer than they appear. Well, if you have a wife, or if you've ever had a sister, and then you've also no doubt had experience with makeup mirrors, they have the slightly spherical shape to them, so that's for magnification. We're going to see how that's done as well. But remember the law of reflection? The angle of incidence is equal to the angle of reflection about a line normal to the reflecting surface. That is not true of just plane mirrors. That's true of any reflective surface. But the line has to be normal to the surface at that point. Now, if this is a spherical mirror, then the line normal to it at every point is going to be what? Radial. Always going to point, all normal lines will point back to the center of the curvature. Okay? Now that's true whether it's concave or convex. And any light coming in and striking that mirror will reflect at an angle equal, an angle of reflection equal to its angle of incidence. Again, concave. Here. Use the same center point. Convex. And I drew it concave, didn't I? Which means the center point is now over here. But the normal lines are still radial to that curvature. So now, they go into this quite a bit in the book, and I do recommend you read through it and grasp it. They're going to talk about how, in the case of a spherical mirror, you're not going to get a true image. Because in order to get a true image, all of the light reflecting in has to come to a very well-defined focal point. Well, in fact, in a spherical mirror, that's not going to happen. And it's going to cause what's called spherical aberration. Rays coming in way up here are going to focus, and you'll see it when you start looking at the focal point. When we look at the focal points, rays coming in here are going to focus to a point here. Rays coming in here will focus a little bit ahead or a little bit behind. And the same, so there will be this smearing and depth of field of the image. That's called spherical aberration. All I'm going to tell you is that in order to fix it, instead of using a spherical mirror, you would use a parabolic mirror. Okay? That's why satellite dishes use parabolic shapes, not spherical shapes. But if the diameter of the reflecting surface, if the dimension of the reflecting surface is much, much smaller than the radius of curvature, then you can minimize spherical aberration enough that it becomes irrelevant. It becomes negligible. So you can ignore it. And so you don't, as long as you're making very small mirrors with very large radiuses of curvature, then you don't have to worry about making it exactly parabolic. Spherical works just fine. And spherical is a lot easier to make because, basically if you want to make a sphere, you just inflate it. To make a parabola, not quite so simple. I want to define some of these terms for you that you're going to need to know. And I'm going to leave it to you to go through and finalize some of the derivations if you want to see the formal treatment of how these things come about. Because I really want to get through this chapter 2-4 for y'all to be able to attack the homework. Let's talk about image formation and how we do it with ray diagrams. First of all, let me make sure, is there something here? Yeah, there is. I wanted to point this out to you. If we're talking about where light comes in, where it ends up coming to, light coming in parallel is all going to reflect back to what's called the focal point. Okay? And that's where the focal point comes from. And this is what I was saying a moment ago. In the case of a spherical mirror, it's not actually going to be one well-defined line. It's going to be a line plus or minus a little wiggle room based on how much how much spherical aberration there is, and you minimize it by making the mirror smaller in relation to the curvature. As long as the rays are coming in essentially parallel, then the spherical aberration is going to be minimized. Now, what you need to know is that if this is defined as 0, this is defined as the center of the radius, or the radius of the curvature of the mirror, then the focal point is half the radius. So, let me get over here and start with a clean drawing. I'm going to try and do an image formation as best I can. And they do a very good job of it in the book, so you won't have any trouble reading it. Let's talk about this. We've got the center point here, and we've got the focal point here. So this is the radius, this is the focal point. Now, let's put an object. Yeah, they are labeling it C. Okay. Let's put us an object right here. Somewhere between the center and the focal point. Where is a ray of light that emanates from that point? Where's it going to go? It's going to hit there, and then it's going to reflect. It's going to reflect down through the focal point. Now let's take another ray that starts here at the bottom. It's also going to pass right back through the focal point. What about a ray that starts here and passes through the focal point? It's going to come out essentially parallel. See this point? Right here? There is your image formation. Now, you'll notice it's inverted, and it's bigger. It's magnified. What else do you notice about it? Farther back. It's beyond the center, in fact. Light is actually passing through this space, the space that the image occupies. This is actual physical light passing through that space. Unlike the virtual image from the plane mirror that we saw earlier, this is a real image. Okay? Once you understand, once you know, this is how holograms are formed, but I've seen it happen in places as odd as in a bathtub with those, those bezels they put around faucets and stuff, how they're curved in, very reflective chrome curve. I've actually seen real images form in this space right in front of those mirrored surfaces. There's an old gag that you used to be able to buy at the these sciencey stores, like the places where they make those. Every mall has, I don't even know the names of them anymore. What's some of the names of them? Exploratorium or whatever. You used to be able to find them. It would be like two spherical mirrors glued together, reflective on the inside with a hole cut in the top one. You can put something in it and it will create a real image that looks like you can just reach in and touch it. But it's not there. That is a real image of the object that's placed inside the thing. And it's really freaky. Yeah. It's not really that freaky once you understand how it happens. But the first time you see it, it can really mess with your head. Anyway, this is the difference between a real image and a virtual image. If light is actually passing through the space of the image, it's real. If light is not actually passing through the space of the image, it's virtual. Now, this is your focal length. This is the distance to your object. This is the distance to your image. What you are going to need to know is that, this is the height of your object, and this is the height of your image. You'll notice if the height of your image is negative, it means that your image is upside down. What you're going to need to know is that the height of the image divided by the height of the object is equal to, and I've turned it over, so I'm just going to, it's equal to the distance to the image divided by the distance to the object. All right? They go through a derivation here that I will refer you to study it, to read through it, and understand it. But it all boils down to this mirror equation. And this is what you will use to work the problems. 1 over the image distance plus 1 over the object distance is equal to 1 over the focal length. All right? This is the mirror equation. They derive it in the book. In the case of the spherical mirror, it is true for every reflective surface, regardless of geometry. Whether it's a plane mirror, a parabolic, spherical. Now, one more thing we're going to talk about is the magnification. Magnification is equal to the height of the object, or the height, how do they write it? Which way do they put up and down? The height of the image divided by the height of the object. Is your magnification. And that will be equal to the minus the distance to the image divided by the distance to the object. Okay, and again, the sign convention here is that if the image height is positive, it's upright. If the image height is negative, it's inverted. And D and I, the distances either to the image or the object, if it's positive, it's in front of the mirror, and if it's negative, it's behind the mirror. So the image or the object, either one. Now, how could the object be behind the mirror? No. No, but it's going to, you need to remember that. I told you 24, I think it is, the problem number is the one that's going to give you trouble when you finally figure out how to do the quadratic equation and get it set up and you solve it. You're going to have two solutions. One of them will give you because when you do the ray diagrams here, we call that the object, which gave us this for the image. But they're completely reversible. We could just as easily call this the image, and that would make this the object. And the mirror actually works that way. You can, if you've got a mirror that you see a magnified image here, you'd see a magnified and inverted image here, you'd see a smaller object right here. If you take that same object here, move the object here and make it this size, then you'll get this image over here. Well, when you solve that quadratic equation, one of those solutions is going to say, oh, what you're saying is if I have an object behind the mirror, then it would produce an image here at this position. But it wouldn't because light can't pass through the mirror. That's actually not true. Even the best mirrors are only 99, 95, 99% reflective. There's some faint trace amounts of light will pass through. Yeah. That's another thing. Some mirrors are mirrored. Mirroring is applied to the back of the glass. Other mirrors, the mirroring is applied to the front of the glass. And it isn't always absolute certainty. But if you think that you might be in a room where you're being observed through that big giant mirror on the wall, and you're not sure if it's an actual mirror or if it may be a two-way that someone's got a camera behind it, walk up, touch the mirror with your fingernail. If the image and the fingernail touch, then you've got the mirroring on the front side of the glass. And there's a really good chance there's a camera on the other side or someone. If you see a space between the fingertip and the reflection, it'll be equal to the thickness of the glass and the distance between your fingertip and the reflective surface. If the mirroring is on the back of the glass, supposedly, then it's probably just a plain mirror. No, not twice. I will. All right. Here's an example they use of a concave mirror. Just use the same one here. There's our center. There's our focal point. Now this is where you start getting into these makeup mirrors, the magnification and stuff. Well, you see that you can have magnification with that was a concave mirror, okay. Oh yeah, that's the point I wanted. That's a point you do need to know, is that if it's a convex mirror like that, then the images will always be virtual. You cannot get a real image from a convex mirror. And if you think about it, it makes sense, because all the light that hits it is going to reflect outward. And since it's reflecting outward, it cannot all head to a focal point. It will all point to a virtual focal point somewhere behind the mirror. But with concave mirrors, you absolutely can get real images, and like I pointed out, they can be really bizarre. How would you get a virtual image in a concave mirror? You put the object between the mirror and the focal point. Ray from there passes out, passes through the focal point. Ray from here passes through the focal point. Ray from the focal point passes through here and reflects out that way. They do a better job of it here, but oh yeah, the other one is from the center to the tip, passes here, goes out. Point is, all of these lines end up coming out here and pointing to a virtual image. But you'll notice that that virtual image is not inverted. If you have if you put the object distance in between, if you put the object between the focal point and the mirror itself, then you will create a virtual image that will be upright. Of course, because all of this is completely reversible, and this is what matters to that problem that's going to give y'all trouble. If you put an object back here, mathematically, by the ray tracing, it would produce this image here. Okay? So physically you can't do it because you can't get light from here through the mirror, but mathematically it would still work. And that's the second solution in that quadratic equation. If you work it out and you actually do the arithmetic, you'll find that that second solution produces a negative object distance. Yeah, the last thing I want to talk about is the index of refraction. There's a list of them here on the table. And all it is a ratio of the speed of light in a vacuum to the speed of light in the medium, whatever medium it is. Okay? Index of refraction is going to be important next week when we get to Snell's law. But today, what you need to know is that the index of refraction is equal to the speed of light divided by the velocity of light in the medium, where c is the speed of light in a vacuum, or in free space, and v is the velocity or the speed of light in whatever medium the index of refraction applies to, whether it's glass or Lexan or air. Actually, the speed of light, the index of refraction for air is very nearly 1. I think it's like, well, it should be here. Yeah, it's off in the 4th decimal place. It's 1.0003. So the speed of light in air is pretty much 300 meters per second. Okay, but you notice in some of these it changes quite a bit. Diamond is the worst. It slows down huge in diamond. And it has to do with how much light will bend when it passes through the interface to that medium. But that's getting into Snell's law, which is next week. Do any of you have any questions about what we've covered so far? All right. Good luck, and I will expect plenty of homework questions next week.